Poing is a dynamic model of protein folding written by Dr. Ben Jeffries in our lab. It relies on a simplified representation of a protein to permit fast simulation times, and through the use of a novel solvent model, proteins undergo rapid hydrophobic collapse. In Poing, a protein backbone is represented by a chain of alpha carbons, shown here connected by a thick black line. Side chains are reduced to a single particle characterized by its size and hydrophobicity. Within the Poing system, monomers in a protein are bound together by linear elastic springs. Each spring has an associated stiffness and equilibrium distance assigned to it, on either physical grounds or by trial and error testing. The dynamics in Poing is driven by random bombardment by notional solvent molecules using the Langevin equation. Langevin is essentially a rearrangement of Newton's equation with two extra factors. Drag, represented here by gamma v, which simulates the slowing of particle motion by the drag of the surrounding solvent, and r, which denotes a random bombardment vector from individual solvent molecules. The solvent model in Poing involves bombarding exposed hydrophobic residues with greater frequency than exposed hydrophilic residues. This leads to rapid hydrophobic collapse. Secondary structure predictions are used to add springs that encourage the structure to adopt alpha helices and beta strands. Dynamic springs representing backbone hydrogen donors and acceptors exist midway between each alpha carbon monomer, allowing beta sheets to zip up and unzip during simulation. Finally, side-chain steric interactions are modeled by spongy spheres determined by the average likelihood taken over all potential rotamers of an atomic clash. In the published work on Poing, we investigated simulating protein synthesis from a virtual ribosome into a crowded cellular environment. In Fire 2, we don't use crowding, but we do use synthesis from a virtual ribosome. Just like Fire in normal mode, a set of potential models of your protein are constructed. In intensive mode, models are selected by heuristics designed to optimize both coverage of your sequence and confidence. These models constitute a set of distance constraints between residues in your protein. Each distance constraint is represented by a spring, and your protein is synthesized by a virtual ribosome in the context of these springs, creating a model that aims to satisfy as many of these template-derived constraints as possible. The methodology behind Poing was published in 2010 in the Journal of Molecular Biology. The multiple template applications have not yet been published. Now we can see some movies of Poing in action. Here's a real-time simulation of a small all-alpha protein by Poing. Here you can see the points in the model that are simulated and the most basic forces which keep the model protein together, shown as rods between the points. Black rods are repulsive forces, and white rods are attractive forces. Here we see the spring forces that maintain the predicted secondary structure, in this case alpha helices. Here we see a much larger 120 residue all-beta protein. The forces displayed here are the hydrogen bonds holding the strands in the sheet together. The key driving force of the dynamics in Poing is the random bombardment by notional solvent molecules, here shown by cones indicating the direction of the bombardment. Here we see the same molecule, but this time in a surface representation. The small blue dots indicate the parts of the surface being bombarded by solvent over time. Here we can see all these forces working together to drive the dynamics of the protein folding. This is a small all-alpha protein being simulated by Poing and rendered on the screen at twice real modelling speed. And now at 4 times real modelling speed. After some time, the topology of the protein settles down. This is a much larger 120 residue all-beta protein, being rendered here at twice real modelling speed. If we speed up the simulation to 4 times real modelling speed, we can start to see sheet formation. You see the purple strand starts to hydrogen bond to form another sheet, and these two sheets come together to form a sandwich. In this simulation, we see a large red sphere representing a virtual ribosome, and we can see the growing protein chain, currently tethered to the ribosome, as it is synthesized into a crowded cellular environment. Crowding molecules are represented as translucent spheres, and these are prevented from floating off into space by the larger lined containing sphere. In fire, we don't use macromolecular crowding, but we do use the virtual ribosome and resynthesize your protein in the context of springs that have been derived from potential template-based models. Poing is available open source on SourceForge. Just look at the links in the Fire 2 help pages. Thanks for watching.